Okay, let's continue our conservation of matter discussion with molar mass now. So to begin things, we have to understand first what is mass. So a common misconception is that mass and weight are the same. They're not. They're not the same, but they are related to each other. Okay, they're very similar. Your mass measures the amount of a sample. Okay, the amount that you have present. And the way that we do that is by comparing it to a standard value. So the image of a scale comes to mind. We compare this to a standard. For example, if I want to know that I have exactly 1 pound, okay, so that's a weight unit, what I would do is I would put a 1 pound object on one side of the scale, and then I would add whatever the other substance is up until my scales balance. So I'm measuring how much is there, how much mass is present by balancing it. So that's the first thing to be aware of. We typically measure mass in the unit grams. Now what we're going to discuss though is another way of figuring out the amount of a sample. And that is by describing it in terms of the number of moles or the number of molecules, right? Remember the word mole represents a set number of molecules, 6.02 times 10 to the 23rd molecules. Okay, so in this case, we're not comparing to a standard. What we're doing is we're counting exactly how many particles are present. Okay, so moles or molecules tell us how much we have exactly by counting. Moles are exact numbers. Mass, these are compared numbers. Okay, so we want to count exactly the number that are present. So here you notice that we've labeled every bean has its own number. We have exactly the 16 beans shown. Okay. Now, the way that these things relate to each other is that if you know the molecular weight, okay, in the UK they tend to use this term molecular weight. Typically we're going to describe it as molar mass, but these are the same thing we're describing. But the molar mass tells you exactly what the counted number is based upon a measurement. So we've got some relationship. We'll say that here are 16 beans is going to measure 1 gram. Okay, so let's just say that equivalence is true. What we can do is we can think about that and say, oh, well, if I measure 2 grams, comparing these to each other, I must have 32 beans. So that's the general idea. Now, what we can do, like the way that we use this in a chem lab, is we can put a sample on a balance and we can get its exact mass, which will tell us pretty precisely how many moles or molecules we have. Now let's discuss how do we determine this number. What we do is we're going to use the average atomic mass from the periodic table. So looking at the periodic table, we see all of these mass numbers, the average atomic mass. Now it's actually very, very reliable for us to use this mass number because this factors in all of the potential isotopes that you would find in a sample. Okay, so our average mass is the number that we're going to use to figure out how many, what mass is equivalent to how many counted molecules or moles. So if we're talking about 1 atom, okay, super small scale, so 1 carbon atom, that has exactly 6 protons and 6 neutrons, so that isotope is our standard, remember, that has a mass, okay, of 12 atomic mass units, AMU. But we don't ever deal with 1 atom specifically. Instead, we always work in a much larger scale. So instead of talking about 1 atom of carbon, we're going to say we want to know 1 mole of carbon. And the beauty of this is the average atomic mass that's shown that is going to be the number of grams. So 1 mole of carbon, if we take the average isotope, because it's not going to be one specific atom with exactly a mass of 12, it has to have an average of 12.01 grams. Okay, 12.01 grams in one atom of carbon. Now, a lot of the time we're not dealing with a specific atom though, we're dealing with a compound. And remember, a compound is 2 or more atoms that are bound together. So to find the molar mass or the molecular weight of a compound, you have to take the sum of the individual atomic masses. So an example of that would be you're given the O2 molecule. What you have to understand is it's the sum of the individual masses. So the way that I like to write this is oxygen has a mass of 16.00. That's the average mass, 16.00 AMUs. But I don't have one oxygen, I have two, so I'll multiply that value by 2, and we find that an O2 molecule has a molar mass of 32 atomic mass units. But since I don't want to think about atoms, I want to think about moles. Instead of 32 AMUs, this is 32 grams of O2, and that is equal to 1 mole of O2. Now let's practice this idea. So I'll assume that you've taken the time, you've paused the video, and now we can move on. So the mass and the moles tell you the blank of a sample being measured. Mass and moles tell you the amount, how much stuff. Mass is an amount that is compared to a standard value. So we can put it on a balance, remember, using a standard weight. Moles and molecules are not compared. Okay, so this is different. They are exact, okay, or counted units. Exact or counted units. The molecular weight, or the molar mass, allows us to count the number of pieces or particles by weighing them. Now find the molar masses of the following. So what I will have you do is think sodium to start. Sodium, if you look back on the table, you see it is 22.99. So the molar mass in terms of grams would be 22.99 grams. F2, we're going to look at our fluorine. 19.00 is the mass. So we have to take our 19.00 times 2 gives 38.00 grams in an F2 molecule. Or in it, I should say, in a mole of F2s. In fact, what I'd like you to do is just think about those in these terms. 22.99 grams per 1 mole. Grams per mole. H2O, hydrogen, if you look on the table, is 1.01 times 2 is 2.02. Oxygen is 16.00. Combine those and you get 18.02 grams per mole. Now, MgS, magnesium, you see is 24.31 and sulfur 32.07. So 24.31 for magnesium, sulfur 32.07. We'll add these up and we get 56.38 grams per mole. Carbon dioxide, CO2, carbon 12.01, oxygen 16 times 2 is 32. Combine these and you get 44.01 grams per mole. H2SO4, hydrogen 1.01 times 2, sulfur 32.07, oxygen 16 times 4. So what we have here, this is going to be 64 and 32 and 2.02. So that's 66.02, 66.09, 68.09, and 98.09 grams per mole. Now the NO3 are nitrogen, 14.01. So nitrogen 14.01, oxygen is 16 times 3 gives 48. And lastly, let's see, so 14.01 and 48, that's going to be 62.01 grams per mole. All right, hope that helped.